So question 4, citric acid, that's in citrus fruits as opposed to uric acid, that's present in urine. This question's very standard, every year this comes up. So a conjugate acid-base pair, you're looking for two chemicals, one reactant, one product, and they are different by H+. So looking at this, I've got the citric acid on the reactant side and this chemical here on the product side, and they're different by H+. So you could have those two chemicals as an answer, or the remaining two, water and the hydronium ion, are also different by H+ and on different sides of the equation. Well, most people could do that, so don't feel too clever. For AII, the equilibrium constant. Now, it's a weak acid, and my answer was because Kc is small, but the IB wasn't going to give you that answer this year. It has to be that Kc is less than 1. Okay. Let me just recap what Kc is. So Kc is an equation that shows the concentration of the products over the concentration of the reactants. So if Kc is less than 1 or small, that means that whatever numbers at the top are going to be small compared to the numbers at the bottom. Going back to the equilibrium, that means that the product concentration is small compared to the reactants. Well, it's this H3O+, this hydronium ion, that's responsible for acidity. So hardly any of those H3O+ ions are produced, so it's a weak acid. Excuse me. Or you could just say it's a weak acid that's partially dissociated. That's also an answer that will get you a point. For AIII, again, there's a question, and there's the same old tricks just trying to reel you in here. The only thing that changes Kc for a specific equation is temperature. So their first question is, well, does changing H+ change Kc? No, because the only thing that changes Kc is temperature. It's a little trick, because where's the H+ in that equilibrium? Well, okay, the H+ is just another way of writing H3O+. If you think about it, H+ in water is really just H+ and H2O, which is H3O+. So it's a little trick, but not too bad. You should know that. Now, if you increase the temperature, okay, now Kc changes, because temperature is the only thing that changes Kc. If the temperature goes up, well, the question says that the reaction is endothermic in the forward reaction. It's endothermic. So I like to put plus cold, which must mean the reverse reaction is exothermic, plus hot. So if I increase the temperature, Le Chatelier's principle, where a system in equilibrium when stressed will move to oppose the stress. Well, if I'm heating it up, it's going to want to cool itself down, which means it goes to the cold side. So the equilibrium will shift to the right, but you still don't have your point, because they want to know the effect on Kc. Well, if it shifts to the right, there's going to be more cold, whatever that means, but there's also going to be more of this, of the products. There's going to be more of the products. And that means that this number is going to get bigger, the number at the top, which will mean Kc will also get bigger. So Kc increases. Kc increases. And 4b, standard question. It's normally 2 points. It's only 1 point this year because I don't want an explanation. How can you determine experimentally if it's a weak or a strong acid, assuming the concentrations are the same? Well, the weak acid has a higher pH than a strong acid. A weak acid has a lower conductivity, and a weak acid reacts slower with a chemical. And this year you had to say a specific chemical. So a weak acid will react slower with magnesium or calcium carbonate than a strong acid. You don't need to give the explanations. And if you're also looking at the mark scheme, you'll see there's some confusing stuff there as well. That's the high level answer. Well, what you do in an SL test if you're HL, give the SL answer. Okay, that's question 4 done. Question 5 is to do with electronic configurations. Now, there's two atoms, or two elements that have electronic configurations that don't fit the pattern, chromium and copper, and yet they've asked us about the copper plus ion. Okay, so I'm going to do copper first, Cu, and then I'll make it copper plus. Only 40% of the people got this right. So copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. So it doesn't follow the pattern. You've got the 4s1 there. Because the 3d10 is more stable than the 3d9. But that's beyond the scope of this question. All right, now I want to make it copper plus, which means I'm going to remove an electron. And there's 4 shells, 1, 2, 3, 4 shells. And you remove electrons from the outer shell first, which is the 4th shell. So that is gone. So that's the answer there, without that 4s1. 5AII is to work out delta H. Well, in SL, there's 5 ways to work out delta H. You can use the enthalpy or energy diagrams, Hess's law, delta H is MCAT, MC delta T, bond energies, the makey-breaky, or this way, the products minus reactants for the heat of formation. So the heat of formation data is in table 12, so it's this, that's what the F means. So I'm just going to take the numbers from the table and put them underneath. Now it's going to look like some numbers are missing. In fact, I was called out of my class once to go to a chemistry exam, an IB chemistry exam, because they thought there'd been a mistake. No, no, no. Everything's there. The hydrogen chloride is minus 92.3. So I need 4 of those. 4 times minus 92.3. Oxygen and chlorine, both elements, are not in the table because it's 0. The standard heat of formation for any element is 0 in its standard state. And water, there's a little tricky trick there. Water appears twice. I want the gaseous one. So that's minus 241.8. 2 times minus 241.8. Okay, now you just have to do products minus reactants. So delta H is going to be the sum of the heat of formation of the products minus the sum of the heat of formation of the reactants. That sentence itself would just give you 1 point. So for products, I've got 2 times minus 241.8 minus 4 times minus 92.3. So that gives me minus 114.4. Oh, I don't think I'm going to be bothered with the sig figs and stuff like that. That's more bother than it's worth, I think, in this question. Yeah, that's the answer there, just straight out the calculator. And the units, the IB says is kilojoules. Interesting. That's wrong according to their answer scheme. I think it's kilojoules per mole. Interesting. Alrighty, so 1 point for the calculation and 1 point for that setup there. Next question. So the activation energy is bigger than the catalyzed activation energy. Oh, that's a terrible line. So that's going to be the EA cat here. And the catalyzed activation energy has to be lower than the actual activation energy. So that's EA cat there. And yes, you can have negative activation energies. That's beyond the IB. Alrighty. That's 2 easy points for that. How does a catalyst increase the rate of reaction? So, not many people got 2 points for this. So it increases the rate of reaction. Well, it reduces the activation energy and provides an alternate reaction pathway. That would be my answer. Yeah. That's the answer. Excellent. You could also say that with a reduced activation energy, more particles have enough energy to react. They give you that as well. Next one. All right, 5b. So the equation is hydrated copper chloride with X water, and well, they drive the water off, don't they? So X water is going to come off, and you've got your copper chloride left over. So you can solve this just using the regular moles mass, molar mass, and the boxes method. So I'm going to have my moles here, my mass here, and my molar mass. Now, if you can do it without all this palaver, they'll give you full points if you've got the correct answer. And if you're not sure, just guess a number. In this case, the number's 2. Let's see if we can get that. All right, so I'm going to fill in some boxes. I know the molar mass of water is 18.02. They were fussy with the decimal places in this question. Sometimes they let you off. It doesn't look like they would in this one. And I know that my hydrated copper chloride, I had 18.360 grams of it. I've got to take off the mass of the crucible, though, don't I? So that's 16.211 for the crucible. So that gives me 2.139 grams of the hydrated copper chloride. And how much of the dehydrated? They've driven the water off. Well, that's 17.917 minus 16.221. So that's going to be 1.696 grams. What else do I know? By conservation of mass, I know the mass of the reactants has to equal the mass of the products. So I can work out the mass of water. That's the difference between those numbers there. So the mass of water so that's 0.443. All right. I can work out the moles. Don't forget moles is mass over molar mass. So the moles of water is 0.443 divided by 18.02. So that's going to give me 0.0246. That's to 3 sig figs. Those sig figs aren't mentioned in the question. All right. People attempted to fill that box in. You don't know the value of that because you don't know the value of X. So you can't fill in the molar mass. We can do copper chloride though. So copper is 63.5 and chlorine's 35.45. So 63.5. Oh, 5 watt. Bugger. 5. So 134. 0.45. So I can also work out the moles of copper chloride now. So that's going to be moles is mass over molar mass. So that gives me 0.0126. All right, now we're going to use just a simple mole ratio. 1 is to that as x is to that, and I can just solve for x. So 1 is to 0.0126 as x is to 0.246. So that gives me x equals 0.246 over 0.0246, excuse me. One, 2, 6. It's about 2, isn't it? Yeah, so that's going to give me 1.95. Now 1.95 is possible. It doesn't have to be an integer. They'll accept it, but they were hoping you'd put 2. So 1.95 or the integer of 2. All right. Next question. 5CI. This question again comes up every year. What conducts the current? Well, in the wires, it's the electrons. And in the electrolyte, that's the molten ionic compound, it's the ions. So each of those was worth 1 point each. The next question, the IB complained that some people left it blank. I don't know what to do with that information. In SL, electrolysis turns the ion into the element. So if you've got platinum iodide and you electrolyze it, you get platinum and iodine. Now in this case, it says that this electrode here, it's the positive electrode. What are you going to see at that electrode? Well, the negative ions from the copper 1 chloride are going to go to that positive electrode. So I'm going to have the chloride ions, and it always makes the element, Cl2. Chlorine's diatomic. How can you remember that? Well, you've got Brinkelhoff, haven't you? Brinkelhoff. Each of these is diatomic. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. I've got to balance that equation. It's not an equation otherwise, so put a 2 there, and we take off a couple of electrons. A lot of people don't like the -2 electrons. Okay, well then let's just put them over here then. There's +2 electrons. There we go. Question 6. Only half the people could do this. You didn't lose any points for the state symbols. So I'm going to make nitrogen, N2, and carbon, that's just C on its own, and water. To balance that out, I'm going to need a 2 there and a 3 there. Now, even though state symbols weren't needed, the examiner's report complained that some people put C2. There is no such thing as C2. C60 exists, but you're not making Buckminster Fullerene there, are you? Okay, so that's question 6A. For 1 point, balanced equation. Now you've got to do a little bit of stoichiometry. Okay, we can handle that. So we're going to do the boxes method. So I've got moles, mass in grams, and molar mass in grams per mole. Calculate the total number of moles of gas produced from the decomposition of 10 grams of this chemical here. So I've got 10 grams of that, and they want to know how many moles of gas. Well, you've got to know that nitrogen's a gas. You're breathing it now. And isn't water a liquid? Well, no, in this case it's a gas because in the question it says water vapor. Alright, well let's hope that the molar mass of this chemical is not too bad. Oh, it's not there, it's not given. Alright. So the molar mass of that guandanium nitrate is 122.11. Nice. So moles is mass over molar mass. So the moles is 10.0 divided by 122.11. So that gives me 0.0819. 3 sig figs there. Well, what are we going to do with that? That isn't the answer. Because now I know how many moles of this I've got. I need to work out how many moles of the gas I've got. So this is going to be twice 0.0819. And this is going to be 3 times 0.0819. Because 1 is to that, as 2 is to that, as 3 is to that. So my final answer is going to be 5 times 0.0819, which is going to be 0.409 moles to 3 sig figs. Did anyone get that right? Only 40% of people got that right. So if you can do simple stoichiometry from like the first week, you're doing okay. Calculate the pressure. There's a couple of pressure equations. Which one are we going to use? This is (6A)II. If it's a standard temperature and pressure, we've got to use that 22.7. Or was it 22.4? Let's hope it's not that. I'll have to look it up in the data booklet. They give me a temperature and a volume, and they want to know the pressure. Well, I've got the moles, so it has to be the ideal gas equation. PV equals nRT. If you want me to know the pressure, that's N times R times T over V. The number of moles of gas is from the question above. If you don't know the answer to the question above, just make up a number, just say 1 mole. You'll get error carried forward. The gas constant is 8.31. And the temperature, don't put 127. That just seems like a weird number, but you know why? That's because the temperature, you're going to be adding the 273, aren't you? That's the cheeky bit there. And divide by the volume. The volume is 10.0 decimeters cubed. Okay, so the minor traps to avoid here are, don't forget to add the 273 for the Kelvin. And if you're going to use 8.31 as your gas constant, you better make sure that you're in decimeters cubed here, which we already are. So that's not too bad. The answer will be in kilopascals. So let me just work that out. So I get 136 kilopascals. Gosh, didn't even need the units. But if you're using 8.31, you're in kilopascals. How many points for that? Just 1. Oh man. 1.5 minutes per point. Okay, so this is one of the hardest questions on the paper. The 3 answers, the 3 points were, well, you had to mention that water has the intermolecular force of hydrogen bonding, and nitrogen has the intermolecular force of London dispersion forces. That was 1 point. The water has the stronger intermolecular force. The hydrogen bond is stronger than the London dispersion forces. So that got you 2. And the 3rd point, well, in an ideal gas, the gas particles will bounce off each other. If the gas particles don't bounce off each other but start to stick together, that's not an ideal gas, and you can't use the ideal gas equation. You're kind of making a liquid there. It doesn't really work, does it, when the gas particles stick together? So which gas particles are going to stick together most likely to? Well, the water ones. And why do the water want to stick together as you cool it down? Because they've got strong intermolecular forces, the hydrogen bonds. So there's your 3 points. And 6b, you're making nitrogen gas and sodium with your other airbag. Well, that's kind of exciting. Suggest including an equation why the products of this reaction represent a safety hazard. Well, the nitrogen it actually does pose a safety hazard, but that isn't the answer they're looking for. It's a really exothermic reaction, so when the nitrogen gas explodes with the bag, you do sometimes get a minor burn on your face. So there's a little bit of a safety issue there. But that's not the problem, is it? It's the sodium. My God, the sodium. So sodium reacts with water. You're 70% water. So that's got to be the issue here. So what do the IB want? Sodium plus water goes to sodium hydroxide and hydrogen. Oh, sodium hydroxide is really nasty. It corrodes the skin as well, so it's all round unpleasant. Now, it was possible to have a good answer and be wrong. For example, if you said that the sodium was reactive or dangerous, you wouldn't get the point. You had to say that either sodium reacts violently with water, we said that, it's highly exothermic, so it gives off a lot of energy, so it could burn you, and the hydrogen that's also produced is explosive as well. All right, that's the end of the paper. Another one done. Oh, I think I'll try a high level next.